This is part of the series of online presentation materials for the WRF modeling system. This talk is how to use the WRF registry. The WRF registry is a standalone text file that the user is able to edit and modify. Most of the development for WRF requires that the registry be updated to allow the user to introduce new code into the modeling system. The registry controls the names of the variables that are inside of the model. It controls information such as number of time levels, the order of the dimensions, the dimensionality of variables, whether or not variables input or output, how variables are handled for nesting, and the way that the variables are treated when they go into a netcdf file. The registry is going to be required for anyone who's interested in doing serious development on the WRF modeling system. For a roadmap for new users, there are a few presentations that should be taken in order before any of the other talks. These include the introduction to WRF, the fundamental capabilities of WPS, the description of the general functions for real, and then the running WPS and setup and run for the WRF model. There are two other longer presentations that are split into a couple of pieces. The fundamentals in atmospheric modeling and overview of physical parameterizations can be taken as a single lecture. And also the physics part 1 and 2 can also be taken together as essentially a single lecture. The rest of the presentations can be done in any order. This is a software engineering presentation, how to use the WRF registry. It has a companion presentation, also software engineering oriented, the WRF computation. The registry talk is going to consist of two parts. This first part discusses the actual fundamentals of the registry file itself. We'll go over what the registry file is, where it's located, the way that the registry works via the syntax, and then go over the important 3 keywords that are used in the registry for nearly all modifications to the WRF file. Part 2 of this presentation is utilizing the information from part 1 and going through a list of examples. The WRF software is designed to be in 3 layers. There is a top driver layer, there is a middle mediation layer, and then there is a lowest level model layer. The driver layer is really a framework. It deals with decomposition of variables. It is the component of the modeling system that allocates space. The mediation layer has to know a little bit about what the driver is doing. It has to know a little bit about what the model is doing. The mediation layer is responsible for setting up the algorithmic steps to conduct a single time step of the model. The lowest level, the model level, is where scientists would feel most comfortable. This is where all of the physics and all of the dynamics live. This is the portion of the model that does not really care how the framework or the driver is handling issues such as parallelization. Off to the side of the compiled source code that constitutes the WRF software is a separate directory called the registry directory. Inside of this registry directory, there are a number of files, and generically we're just going to refer to it as the registry file, even though there are about a dozen of them. This registry file is a text-based file that's used for both the real program and WRF. We've mentioned before that the real program and WRF are very tightly coupled together. They share the same source code and they share the same registry file. The registry file is an active data dictionary. Any changes that are put into the registry are put into the WRF source code via CPP directives. This amounts to automatically generating source code, and a very large amount of source code. Approximately 400,000 lines of source code are added during the build of the WRF modeling system. The lines that are added are those lines that are typically very prone to errors. The registry controls a number of attributes for individual variables, whether or not it's input or output, how communications are handled for it, the way that nesting proceeds, how many time levels it has, whether or not they're staggering. There are other capabilities that the registry is tasked with. All of the communications inside of the WRF model are handled via the registry. All of the namelist options are defined inside the registry, and actually hundreds of additional namelist options that are not in the namelist.input file are defined inside of the registry. This may sound daunting, but it's actually apparently very easy. The registry itself is 3 times the size that it was from its initial release. So a number of developers have been able to put a large number of fields inside of the registry. Anytime the registry file is changed, that means there's been an attempt to modify the source code in the WRF model. Any change to the registry means that a user is required to go back, completely clean the source code, and run configure and compile again. There are a number of registry files that are original registry files that a user may modify, but traditionally for ARW, it's the registry.em_common. Any changes to the generic file named registry, which is generated during the processing of the registry file, those changes would be lost. All of the registry files in the registry directory follow the same sort of syntactical requirement. There is a leading keyword, and then after that keyword, there are a list of options that are associated with that keyword. While there are approximately 10 keywords that are used inside the registry, there are really only 3 that most developers need to be concerned with. The first is dim spec. This is the keyword that specifies the dimensions that are used inside of the WRF modeling system. You would think that having a I, J, and K dimension, possibly an additional dimension for the number of soil layers under the ground, would be sufficient. However, all of the single letter, uppercase and lowercase, and special characters have been used for dimensions, and now the dimensions have spread into using multiple characters. State is a keyword that is used to define arrays and variables that are inside of the domain structure. The domain structure includes variables that are meteorologically oriented, wind, temperature, moisture, pressure, associated with the projection, such as latitude, longitude, variables that came from GeoGrid, such as the static information, topography, land categories. Information that is utilized by the WRF model for individual sizes of domains, grid distances, etc., are all defined in the state. The current date, the time step, the grid distance, the number of vertical levels, the spacing between the levels, all of those are state variables. I1 is similar to a state variable. This is a variable that is only allocated during a single time step of solve. So I1 variables tend to be local to the solve routine and routines below it, and they only live for a single time period. These are fields such as tendency arrays that don't have to live from one time step to the next. There is a typedef keyword which allows WRF users to define derived types. Of these, the only important one that we really have users care about are the state arrays. These are the arrays that allow a user to put information into the model or take information out of the model. If any variables are going to be communicated, they must be state arrays. This slide shows the remainder of the keywords that are used inside of the registry. rconfig has the mnemonic runtime configuration. For the WRF model for the real program, the runtime configuration is the namelist.input file. Every variable that is in the namelist.input file is defined inside of the registry. Even more, there are hundreds of variables that are not defined inside of namelist.input file, but they are described and defined and have default values provided for them inside of the registry. Package is a keyword that allows the user to associate particular variables with a package. This is handy if you are using microphysics or WRF capabilities such as chemistry. There's no need to allocate space for 10 or 15 additional 3D arrays for a very expensive microphysics scheme if those arrays are not going to be utilized because at runtime a simpler microphysics package was used. Similarly, there's no reason to allocate space for maybe 50 or 100 extra 3D arrays if you are not running a particular chemistry option. The next three keywords, halo, period, and expose, are all mnemonics for kinds of communication stencils and processes that are going on. Halo describes the way that information is set up on the neighboring grid cells where rows and columns of one neighbor are shared with a next door neighbor. Period is very similar to halo, except that for periodic boundary conditions, we have information that leaves the eastern boundary comes in on the western side. Information that leaves the northern part of the boundary comes in on the southern side. The last communication that's used for FFTs inside the data assimilation and others is for parallel matrix transposes. And except for a few specialty cases, this is hardly ever used. Lastly, a keyword very similar to a CPP pound include is simply include, and it lets one registry include information in another registry. In this list, really the only two that we would like to have users be responsible for are rconfig and package. So the big three are state variables, and that's information that you want to go into the model, you want data to come out of the model, or you have data that you know needs to be communicated. rconfig allows a user to define how namelist variables are constructed and used. Package is a way that users can associate new variables with a particular physics scheme. They're really the big three that we care about as far as keywords for the registry: state, rconfig, and package. Let's look at the state keyword. Inside the registry, highlighted in blue here, would be a line where we talk about the skin temperature. The first word is state. It's lowercase, it's case sensitive. And then we have a number of elements that follow that keyword. What type of the variable is it? It's real, or is it logical, or is it a character string? The name of this variable inside of the WRF model, and that would be grid percent TSK. So this is the skin temperature is referred to as TSK. How many dimensions and what are the order of those dimensions? In this case, it's an IJ variable, two-dimensional. Use is typically for differentiating physics variables from dynamics variables. So unless you specifically know that you are introducing an additional dynamics variable inside the modeling system, which is going to have a prognostic equation, which is going to need two time levels, the use is sufficient enough to say MISC for miscellaneous. Again, if it's a physics variable, and most additions to the registry are, the number of time levels of that variable is just going to be 1. Continuing on, the rest of the elements include the staggering, and this can be either the letter X, Y, Z, or a hyphen. An X staggered variable would be the U variables, for example. Y staggered would be a V variable. A Z staggered would be vertical velocity W or geopotential. And hyphen refers to variables that are defined at the middle of the cell point instead of a cell face. So moisture, pressure, temperature. The IO string is overloaded. It includes information for both IO is a variable input or output, what streams is this variable associated with, and also nesting is associated with the IO string. The next three, dname, units, and description. Dname is the name of the variable as it is put in the netcdf file. This name is used inside of the real and WRF model to read in data and write out data. Units and description are also provided, but those are not utilized by the model. So if you make the units kilograms and you would really like to have the units be milligrams, there's nothing inside of the WRF model that is automatically going to scale the variable. The description also is simply just for informational purposes. This registry is an active data dictionary, so the active part refers to the information that you put into the registry that is going to be included inside the WRF model, and it's going to impact source code. For example, how many dimensions does the variable have? Is it real or is it logical? Is it a character string? Does it have a single time level? Where is the staggering? All of these pieces of information will modify the WRF source code. The dictionary, data dictionary part of this is that there are portions of the registry that are actually the final arbiter of what is actually going on inside of the WRF model. So it is convenient to put in units and description that will help you remember what was going on inside of the WRF model when you put this variable into the registry. We mentioned that the IO portion of the registry is overloaded. It handles both pieces of information for input and output, and it also brings in information for nesting. There are 3 letters associated with the input and output. I is an input variable, H is history, so an output variable, and R is for the restart file. There's only a single restart data stream. There are multiple input and multiple history I/O streams that are available. IR and H can appear in any order. They do have to be lowercase. H and I are allowed currently up to 25 different streams. So for example, the WRF input file, the WRF output file are both default streams, and that's stream 0. If you simply have the letter I without any numerals after it, it's saying use the default stream. If you have any other numeral other than 0, the numeral 0 is not assumed to be there. If you would like to have a variable go into stream number 1 and stream number 0, you need to explicitly say the stream 0 and stream 1. If you have a stream that has more than a single digit, for example, stream number 24, you put curly braces around the 24. Nesting information is located also in the I/O stream set of elements. The 4 letters that are used for nesting are U, D, S, and F. U and D stand for up and down, S stands for smooth, and F stands for force. If we want to feed information back from the fine grid to the coarse grid, we are interpolating down scale. If we would like to horizontally interpolate from the coarse grid to the fine grid, that is upscale. If we would like to provide lateral boundary conditions at the end of a parent time step for the fine grid, that is F for lateral boundary forcing. And then there is an option after each feedback to smooth the data inside of the area of the nest, and that's the letter S. The important portion that a user needs to know about the state variable is only variables that are involved with I/O, any type of communication or packages are required to be state. If you have a variable inside of a physics package and it never bubbles out of the top of the physics scheme, those local variables inside physics packages are not controlled by the registry. So the take-home message here is that if you have a variable, and only if you have a variable that needs to be input into the WRF model or in some way output from the WRF model, then that variable needs to be a state variable. Otherwise, it does not need to be defined inside the registry. The second type of entry in the registry of the big 3 that we are interested in users knowing about is rconfig. The mnemonic for this is runtime configuration. Every value that is in the namelist.input file is defined inside the registry with an rconfig keyword. And importantly, we'll see a lot of variables that are eligible to be inside of the namelist.input file are defined inside the registry with rconfig, and they have default values assigned to them. rconfig is very similar to the state entry. It starts off with lowercase rconfig is the keyword, and then there are a number of elements. The first element is what type is this? Very similar to state. Is it an integer? Is it a real? Is it a logical? Is it a character string? The name of the value as it will be in the name list is very similar to the state variables. How the variable is set is different. Typically, what we want user to say is namelist, comma, and then the name of the namelist record that this variable is going to show up in. It is not necessary for the namelist record to already exist. A user could invent their own namelist record. It's not really recommended. We would prefer that if there are variables that belong in the physics namelist record, that they simply be namelist, comma, physics. However, if there are going to be hundreds of new namelist options for a particular scheme, there's no reason to not have your own namelist record. The two really helpful pieces of our config are the number of entries and the default value. Typically, the number of entries is either the numeral 1 or the keyword max dom. If we have a single entry on the domain, on this registry rconfig entry, that means that this namelist value is a single entry, a single value. It is a scalar variable. It's valid for all of the domains. Examples of this would be things like, what is the model top? Default allows you to specify what the value of this namelist entry is going to be if it is not defined inside of the namelist. If it is defined in the namelist overwrites the default value. The third of the big three is the package entry. And we simply show it here because quite a number of users tend to have additional variables that they bring into the model, and we would like to have a good way to reduce the total amount of memory that is not necessarily utilized by everyone. So the keyword entry is package. And you'll notice what the syntax is it says package, and then there is a name, and this is going to be an enumerated constant. So it says, for example, passive QV Kessler scheme. In this case, Kessler scheme is going to be the parameterized value of whatever MP_physics is equal to. And in that line, it's the numeral 1. So if a user asks for the microphysics option number 1, additional moist arrays QV, QC, and QR are going to be allocated and made available for use inside the model. No 4D array is allocated inside of WRF unless it is specifically requested in a package. State variables are always available, though you can include them in a package as well. And if they are on a package line, then they are not available unless they are packaged. But moist variables, chem variables, tracer variables, scalar variables, scalar is a 4D array. None of those 4D arrays, components of those 4D arrays, are available unless they are specifically requested on a packaged line. This is the review of part 1 of the registry talk. What is the WRF registry? It is the text file that accompanies the WRF source code. It is an active data dictionary. It allows, via automatic code generation, hundreds of thousands of lines to be inserted into the WRF source code. The registry controls important characteristics of the model: what data goes into the model, what data comes out of the model, how nesting is handled per variable, how the variables are defined, how many time levels, how many dimensions, the order of those dimensions, what those dimensions are, the name of the variable inside of the WRF model, the name of the variable that's going to be inside of the output stream, how the variables appear in input and output. The way the registry works is via a keyword and option syntax. The initial word on the line is the keyword, and there are three that we care about: state, rconfig, and package, and then just a number of options. Traditionally, what we expect users to do is to go into the source code, find a variable or a namelist value that is very similar to the one that they would like to include. Go into the registry, simply make a copy of that variable, and then add it into the registry. Anytime a change in the registry is made, it mandatorily requires a clean -a, configure, and recompile. This is the outline for part 2 of the registry talk. Part 1 showed us the basic rules and syntax for using the registry, for having an idea of what the registry actually does and how it fits into the WRF modeling system. Part 2 of the registry talk gives us some examples of how to use the registry. Example number 1 is, how do we add output without recompiling? We know that we could add output to the WRF source code by recompiling, by changing the registry. We would simply go into the registry, find the variable that we're interested in, and add the letter H in the I/O stream, and that variable would be included in the output from the WRF model. However, how can we do this without recompiling all of the code? There's a runtime way to do this. What we do is we modify the namelist.input file in the time control section, and we add in a few variables. IO fields file name, and this is a max DOM variable, which means if we have 3 domains, we would need to have 3 character strings, because it would be for domain 1, for domain 2, and for domain 3. And then we have to have the 2 pieces that are always used for IO. We need to know what format the stream is going to be in. 2 means it's going to be netcdf. And we need to know how often that data is going to be output. In this case, we're saying every 10 minutes. These variables are not defined typically by default inside of the namelist.input file. However, we know that since they are in the namelist.input file, they are defined by the registry. So the IO form auxiliary history stream number 24 and auxiliary history 24 interval are both set to 0. If either of those are 0, the WRF model says, if you would like to output something, I'm going to look at what format you have and what interval you would like to output the data at. If either of those is 0, the WRF model knows I'm not going to process this stream. Those have default values of 0 inside the registry. Assuming we do want to have this additional stream, what we can do is, instead of putting data into the WRF model output, the default stream, we can choose any stream we want. We saw that we had up to 25 streams, 0 through 24. In this example, we're showing you how to add data to stream number 24. It's going to be a netcdf file. The data is going to come out every 10 minutes, and the IO fields file name, myoutfields.txt, the contents of that myoutfields.txt file are on the next line, where it says +:H:24:, and then a comma-separated list of variable names. Plus says that we are interested in adding a variable to a stream. H says this is a history stream, so it's going to be output. 24 says this is stream number 24. And then the uppercase list of variable names are the names that are inside of the defined as the WRF in the WRF registry. Similarly, if we would like to remove variables from a output stream, that's also done without recompiling. We also would just say IOFields file name and then the list, the my outfields.txt. In this case, instead of having a plus sign, we would have a minus sign. The minus sign says I'm going to remove variables. H says from a history stream. 0 says this is stream number 0. So this is the default WRF output file, WRF out underscore D01 with a date string attached to it. And what I'm removing are the vertical velocity and 2 components of pressure, because I can get approximately those values in other ways. So this removes 3 3D arrays from my WRF out files if I don't need to have them. So if we are able to output streams or input streams, what streams are we able to use? We said anything between 0 and 24 are available, but a number of streams are spoken for. So typically, streams 10 through 24 are okay. We've already used streams 21, 22, and 23 for things like isobaric data, pressure level, height level data, etc. If you need more streams, there is a single line in the Arch preamble inside of the WRF source code. It simply says max history is equal to 25. If you set that to a larger number, again, clean -a, configure compile, that will allow you to run however many streams you would like to have. The next 2 examples utilize the keywords that we are really interested in users being comfortable with inside of the registry. Example number 2 is adding a variable to the name list. That's going to be the rconfig keyword. Example number 3 is adding an array to the WRF modeling system, and that is going to use the state keyword. So example number 2, rconfig, how do we add a variable to the name list? For us to add a variable to the name list, the keyword is going to be rconfig. The easiest way for us to do this is to look at the existing name list values that are in the name list record similar to what we would like to have. We find a name list variable that is nearly identical to what we want. An integer versus a real versus a logical versus a character string. Do we want a nameless variable that is going to have a single entry, or is it going to have a value that is per domain? We want to know the particular nameless record that this variable is going to be used in. What we do is when we find this, we identify this nameless variable inside the nameless.input file, we go into the registry, and then we search until we find that exact rconfig entry that already exists in the nameless.input file. We make a copy of that line and we just make a small edit. Every time we change the registry, we change source code in the WRF model, but we change it via some CPP directives. So it's important that any time you make a change in the registry, clean -a, configure compile, and just wait for the new executable to be available. Here's the example that we're going to do. We're going to add 2 new variables in the name list. the namelist new variables are going to be called my option 1 and my option 2. My option 1 and my option 2 are both going to be integers. They both are going to go into the time control section. My option 1 will have a single entry. That's why the numeral 1 is there. My option 2 will have an entry for each separate domain, and that's why max_domains is there. They both will have a default value of 0. These are the two lines that I would stick into the registry and then do the clean -a configure compile. While the code is being built, I can determine where is it that I would like to use these values. And once I have these determined where I want to use these values, how do I get the nameless value passed into the routine that I want? There are several ways that you can get nameless entry values in your routines. Any place where you see use module_configure, you have access to my option 1 and my option 2 because the registry program that reads the registry file builds a get and a set subroutine for each of the nameless entries, each of the rconfig entries that are in the registry. So there are hundreds of subroutines that are automatically generated. For my option 1, the subroutine call, if I wanted to get the value, would be call nl for namelist, get or set, and if I want to retrieve it, it would be get, and then underscore the name of the nameless option, my_option_1. There are two entries, or there are two arguments. The first argument is which domain am I interested in? And for us, it's a single entry, so regardless of what domain we put, we're only going to get the single entry. And then the local name of the variable that I would like it returned as. I can also set the nameless option, and I can set it based on a particular grid ID that I would like. And notice in this case, my option 2 has an entry for each one of the available domains, so I have to tell it which domain ID I'm actually interested in setting. Another way that you can access these nameless variables is through this grid structure. A number of the high-level routines up through the solver routine and then even into first RK step where we do a lot of physics, you'll see the variable grid passed in. This is a derived data type. Inside of grid is everything that is in the registry, including all of the meteorological variables, wind, temperature, moisture, pressure, the projection information, latitude, longitude, the static data, the topography, land use categories, sea ice, all of the variables for the 1D arrays, for the vertical structure, for the eta levels, the grid distance, the time step, the date, everything is inside the grid structure, including all of the nameless entries. So if I would like to know the value for my_option_1 and the value or the variable grid is floating around in a subroutine, I have access to it. It's grid percent my option 1. The third way that you have access to the name lists is via config flags. Config flags are the configuration flags, the runtime configuration flags. These are only and all of the namelist entries. Anytime you see config_flags in a subroutine, you have access to the namelist values. Similar to the grid percent, you can simply say config_flags percent my option 1 or my option 2. When you're dealing with config flags, when you're dealing with grid percent, If a variable has multiple entries, one entry per domain, config flags and grid will only show you the entry for that particular domain. What would the changes that we made look like if we wanted to add something to the name list? We asked for 2 new variables to be in the time control section of the namelist.input file. So there's the time control namelist record. We said that my option 1 and my option 2 were going to be the names. So those are the correctly spelled names. We said that my option 1 and my option 2 are both integers. So notice that 17, 1, 2, and 3 are all integers. There's no period and there are no character strings with apostrophes or quotes. We said that my option 1 is a single entry, so we're allowed to have 17 or any other integer we would like to have. We said that my option 2 has multiple entries, as many entries as there are domains. If we have a single domain run and we have 3 entries there, there's not a problem. It simply ignores everything after the first entry. Just like the rconfig keyword allows you to set a runtime option, the state keyword allows you to add an array into the WRF modeling system. This is the second of the 2 big examples, one adding a namelist variable and one adding an array. Very similar to the way that you add an entry in the name list, we add an array by adding a single line into the registry. The registry keywords are either state or I1, and we're going to focus entirely on state keywords here. Just like you did with adding a name list option into the registry, we do the same procedure to add an array into the WRF model. What we do is we determine an array that looks just like the one that we would like to add, and we make a copy of it. So things that we look for. Is this a 1D, a 2D, or a 3D array? How is this variable staggered? Does it look like a U variable, a V variable, W or G at potential? Does it look like temperature or pressure? The staggering XYZ or a dash? Is it particularly associated with a package? For example, is it one of the 4D array indexes? We need to know how this variable is handled. Is it part of input? Is it to be output? Is it a restart variable? We also need to know how it is handled when there is nesting involved. Is there horizontal interpolation to initialize it? Is there lateral boundary forcing? Those are almost always just for dynamics variables. Is there feedback to the fine or to the coarse grid from the fine grid? So here is our array. We're going to make a look for some similar fields that are inside of the registry. So, for example, we could look for the field HDiabatic. That is a 3D array. We could look for MSFT. That's a 2D array IJ, but notice it has some very special ways that it does initialization and the feedback with the letter U. We could look at for the topography field HT. That has also very specific ways that it does nesting. So we, instead of trying to go down the registry and find a field that looks like what we want, the idea is for us, we first go into the WRF model, find the variable that we want to make a new variable that looks like, and then go into the registry and go directly to that line. Almost always the changes are going to be made in the registry directory to this file called registry.corename_common, where corename, for example, is like EM. All right, so the variable that we would like to add is a sum of all of the moisture species. And we're going to call our variable allMoist. We're going to add that into registry.emCommon. This is a real variable, So we set that type to real. The name of the variable inside of the model is going to be all_moist. It is a 3D array with IKJ ordering. That's the way that all of the 3D arrays in the WRF model are handled. This is a physics variable, so the core is MISC, miscellaneous. There's only a single time level, so we make the time level 1. Since this is a variable that is the sum of all the moisture fields have no staggering, horizontal staggering, so we just put a dash in. It's not X, it's not Y, it's not Z. And then the IO stream, the only thing that we're going to do is put in H. We're not inputting this variable. We're going to put this in the history. It's not necessary for it to be in the restart because it's entirely diagnostic. Uppercase all_moist is the name of the variable that's going to appear inside of the netcdf output file. And then we have two extra pieces that are nice to put in just for documentation. The first is the brief description of what this is, and then the second is the units. The brief description and the units are not used at all by the WRF modeling system. The data that we add by putting a single line into the registry for state variables becomes part of that grid structure. And we saw that inside of the namelist.input file. You could say grid % any of the namelist options. The exact same thing, grid % any of the names inside of the registry for the state variables. That grid variable, that derived data type, is inside of the main program WRF. It gets passed to WRF model top. It gets passed down to integrate. It gets passed down into solve interface and into solve. The grid structure, everything that is inside of the registry, including the allocated space for all_moist, is passed into the routine that does a single time step of the WRF model. The solver routine passes variables around, and inside of that solver routine, we have access to the grid structure. The only time that we need to start passing the variable that we want around is when we no longer see grid passed into the subroutine that we want our variable into. So here is the top of, in the dynem directory, top of the subroutine called solve_em.f. Notice that the first argument in that subroutine is grid. So the grid structure inside there is going to be our all_moist variable, is passed into solver. So there's no need for us to declare any new variables, particularly all_moist. There is a call to the microphysics driver, and in that microphysics driver, that's where we're going to dereference the all_moist variable. So the modern Fortran construct is grid % all_moist is the variable that's local to the routine that we're calling from, and the local name of the variable inside of microphysics_driver is going to be all_moist. This dereferencing allows us to take information from the derived data type grid and pass it into the microphysics driver. Once we are inside the microphysics driver, we have a variable all_moist that gets passed in. So because that specific 3D array all_moist is passed into our subroutine, we need to now put the dimensions for this particular variable. The declarations are required. All_moist has the IMS, IME, KMS, KME, JMS, JME dimensions that are used for all of the 3D arrays that are inside of the WRF model. We make it an intent out, so it's clear what's going on. This variable is not input. We're simply summing all of the moist variables, and we're going to put them into all_moist, and we're going to output that. The whole purpose for outputting this is, remember, in the registry, we set the IO string to H. This is going to be in the history. That means this variable can appear in the WRF output file. We can initialize this variable to 0 at the initial time of the model forecast. All of the 1D, 2D, 3D arrays and the scalar constants are set to 0 that are inside of grid. There are a number of flags that go into the microphysics driver. F_QB is a flag that says, does this QV variable exist? So we would add a do loop with an if test that looked like this for each one of the moist species that we were interested in summing. So vapor, cloud, ice, rain, snow, graupel. We simply are saying all moist is equal to all moist plus the value of the vapor. That is all that we need to do to get an array that's filled inside of a physics routine, bubbled up out of a physics routine, and put into the WRF model history file. We make a state variable. That state variable is passed inside of the grid construct into the solver routine. The solver routine for microphysics has a direct call to the microphysics driver, and it is dereferencing the grid structure with a particular 3D array. That 3D array has to be allocated from the called routine, and in this case that was the microphysics driver, and every routine on down. We declare the variable, that it's real, the particular number of dimensions it has, and we pass that variable around. Here's where we fill in that variable, and that's sufficient for us. This initialization of the all moist variable with all the, in this case, vapor, and then we would have if tests for the other moist species, is sufficient to have this variable now be able to be output, and it would reflect the amount of total moist content in the grid cell. Inside the WRF model, there are some specific tools to help developers. For example, if you would like to compute a global maximum, or if you would like to compute a global minimum, or if you would like to know the location of a particular global maximum and minimum, and here global means for the entire domain. That is a little bit tricky inside of a distributed memory job because we no longer have access to every single memory from every single other process. So here's an example problem. We would like to compute just a printout diagnostic. And the idea is that we will output a domain-wide average of the 10-meter wind speed. And along with that, at every output time, we will output the maximum that appears in our domain. And associated with that maximum value, we would like to know the location. So we're going to print out the latitude and longitude. So for the 10-meter wind speed, which is a 2D array, at every output time period, we're going to compute an average of that entire 10-meter wind speed. We're going to also select what the maximum value is and the location of that maximum value. We start this by doing a computation similar to the way that we would do it if we did not have any distributed memory processing going. We simply compute the wind speed, and then once we have the wind speed on our particular MPI processor, we compute the average, and we compute the maximum, and we keep the IJ for that maximum. Then, using some special built-in routines that the WRF model has, the developers are then able to turn those local values on each one of the MPI processes into a value that is the domain-wide maximum, the domain-wide average, the domain-wide location of that maximum. After we've computed all of that information, then we would like to just output this on the master process. Here's what a typical do loop would look like. We are looping over the I and J locations because this is just a 2D array. The P for IPS, IPE, JPS, JPE refers to the patch size. That's the size of our computational domain. We set the wind speed equal to the square root of U and V at the 10 meters. And if it's greater than the previously defined maximum wind speed, then we reset the grab hold of the wind speed value. And if it was larger, we hold on to the indexes. At the end of this do loop, what we have is the total sum of the wind speed, and we can then divide that by the number of grid cells, and that would give us the average wind speed. We know the maximum value, which is max WS, and we know the I and J locations of that, IDX, IDEX, and JDEX. If this was not an MPI job, if this was only a serial processor, we would be done. But now what we have to do is we have to take that information from every one of our MPI processes, send that back to the master process, have the master process figure out the maximum value that's being sent to it, have it figure out the average value that's being sent back to it. So here are a couple of example built-in routines. WRF DM sum real, and this simply says this is a WRF subroutine, DM for distributed memory. We can add up a number of real variables. So every one of the MPI processes will send the total sum back to we send the individual sums to the master node, and then the master node returns from this function the total domain-wide sum. Similarly, WRF DM max val real not only gives us the maximum value, but it returns the I and J index of those maximum values. This is a subroutine. We have more than one argument that needs to be returned. For this example, we specifically chose to require the latitude and longitude be part of the printout. So it is a single call to a built-in function to the WRF model to get a sum of all of the individual local sums from each of the MPI tasks. It is a single subroutine call to get the maximum of the entire grouping of MPI tasks and the I and J index. If we simply wanted the I and J index value of the maximum latitude or of the maximum wind speed, we would be complete. However, we've asked for the latitude and longitude, so it's going to be one more set of usage of internal WRF functions. So this if test at the beginning is the logic that is used to determine which process actually owns that I and J index of the return maximum value. So there was an I and J index that was returned by the master node to each individual MPI process. Each one of the MPI processes says, okay, I know my starting and ending dimension in I, IPS, IPE. I know my starting and ending dimension in J, JPS, and JPE. If the I and J index that is being returned is between those two, I own the maximum, I am the processor that has the maximum value on it. So what we do is we say, set the latitude and longitude, GLAT, GLON, the global latitude and longitude for the entire domain, equal to the latitude and longitude that are defined at that I and J index. If I do not own that grid cell, I'm just going to set the latitude and longitude to a very small negative or a large negative value. So then that allows us to make our second call and say, I'm passing every single MPI process passes back to the master node this GLAT and GLON value, and we ask for the maximum. So the latitude is either going to be somewhere between minus 90 and plus 90. The longitude is going to be somewhere between minus 80 and positive 180. Much larger than the flag value minus 5 nines. So each individual process passes back the GLAT value, and then the master node returns to every single MPI process all the domain-wide latitude and longitude of where that maximum 10-meter wind speed occurred. The last step is now we just output that. If we happen to be on the monitor process, and that's again a function inside of the WRF model, then we can just output, here's what the average value is, here's what the maximum value is, and the latitude and longitude. What that would look like in the RSL output file is, as we would expect, the average value and the maximum, and then the lat-lon location of that maximum value for the 10-meter wind speed. So this particular example shows how to use intrinsic functions that the WRF model is providing for developers to allow you to do global sums, differences, max and min that would probably be a little bit challenging because of the distributed memory processing. This next example is going to show us how we put a number of these pieces together. Namelist values, arrays, and the build structure, and utilizing the capabilities that come from packaging. We're going to add a new physics package, and this is going to be a trivial physics package. It's just going to be a brand new SST that was input. So this is an example of how we could supply a time varying value to the model, but it's also mostly a template to follow if you're interested in trying to develop a new physics scheme. So the specific problem is, let's assume we want to add in a time varying lower boundary condition. In this case, it's the SST for over the water. We're not going to talk about it too much, but there is some I/O that is involved to bring in the SSTs. And we have to modify the WRF model to read in this new state array. Remember, the state array is the variable that is going to be the new variable that is inside our WRF model. State is the keyword inside the registry that says we have a new variable that we're interested in, and we only need state variables if we do only a handful of operations on it. And a couple of those important operations are either we're going to input this data or we're going to output this data. After we do the modification of the registry, what we want to have happen is we want this variable to be available to come into the model on a auxiliary input stream that's entirely controlled by the registry. We would like to pass this new variable into the physics routine, and that'll be part of the grid % construct. And we need to say that we would like to have a namelist option control that allows us to process this data. The state data that we would have in our new variable is going to be called inSST for new SST. So this is a state variable. So this is data that can either come into or go out of the WRF model. It is going to be a real variable. It's SST. The name of the variable inside of the WRF model is going to be inSST. So we will see it referred to as grid % in SST. The SST is a 2D array, so the dimensions are I and j. This is going to be a physics-based routine. This is not dynamics. There are no time levels. So the dynamical core for this is MISC for miscellaneous. The time level is just a single time level. Because it is a mass-based variable, it's a temperature. It's not on a cell face like U or V or W, so the staggering is a dash. When we get to the I/O, this is where things are a little bit special now. We would like to input this variable on an unused auxiliary stream, and we're using auxiliary stream 4. The reason we're using that is this is the way that we put in the SST update capability inside of the WRF model. I4 is input on stream number 4. The name of the variable inside of the netcdf input and the netcdf output file is going to be new_SST, not a very tricky name. The description is the time varying SST and the units are kelvins. Again, the description and the units are not anything that is used internally by the WRF model. So when we add this single line into the WRF model, we are going to have a brand new 2D array that's part of the grid structure. As we saw before, this variable will be defined and allocated and passed inside of the grid structure into the solve EM routine. The dimensions of this variable, because it's 2D array, are going to be IME and JME. It's a 2D array. All the 2D and 3D arrays that come out of the WRF model are memory dimension size. Finally, the last piece that's important here is that this is set up as a variable that is going to have come into the WRF model via an unused auxiliary stream, and in this case, auxiliary stream number 4. Just as we saw before in the previous example of passing in that all moist array, from the WRF to WRF model top to integrate to solve interface into solve, and we pass that into the first RK step part 1, which does the first Runge Kutta step. That passes into all the physics except for the microphysics. That grid percent structure is passed in. Inside of that first RK step, which is where we are here, this is where we dereference our variable, grid percent in SST. So grid percent, that structure was passed into module first RK step part 1. We dereference that so that the surface driver is going to have a local variable named NSST. The module first RK step part 1 has the grid construct, and we dereference the grid construct and pass that dereferenced value into the local variable for NSST. The association of these two variables means that the order inside of the surface driver of those arguments doesn't matter. Inside of the surface driver, now we have that local variable in SST. If we would like to set it up so that not every dynamical core passes this variable in, we can do that. We can make the variable optional. Inside of the surface driver, the paradigm is very similar to all of the other physics driver routines. There is a select case saying, if I would like to know for the surface layer's physics scheme, if the option is new surface scheme, then I'm going to call my brand new subroutine, new SFC scheme. That case value, case parentheses new SFC scheme, that's an enumerated parameter integer. That variable comes entirely from the registry. We check if present because we said that this was an optional variable. If that variable is present in the call, then we can go ahead and process this brand new subroutine. The registry has a package, and now that we've seen that new SFC scheme enumerated constant, this is where it comes from. We say package, and then SFC lay underscore physics is equal to 4. So if their physics for the surface layer physics is equal to option number 4, then we're going to have this new SFC scheme be defined. And that new SFC scheme, that enumerated type, that constant, is constructed by the registry. It's passed into all of the routines, and it's set to the value of 4. So instead of seeing if tests that say if option is equal to 1 or 2 or 3, we are allowed to now say if the option is equal to the new surface scheme. It's very convenient. Remember, anytime that we modify the registry, we have to do a clean -a, configure, and compile. Those changes that we put into the registry allow us to do a few things. First, we said that we wanted to have the input go into the model periodically, and we would like to have that data come in on auxiliary stream number 4. So we see aux input number 4 for the input name, and the interval is every 12 hours. So however often we would like to have the data come in would be fine. Typically, SSTs from national centers are reported about every 12 hours. There may be some linear interpolation between them, but about every 12 hours is typical. The last piece is to make sure that we activate our new option in the physics namelist record. We would have to say SFC lay physics is equal to 4, and this is a max domain entry, so we would put an entry for each one of the domains. An important thing to notice is how the data got into the WRF model. Exactly the same way that we did not have to worry about how the all-moist variable was going to be specifically output. We do not have to worry about modifying the WRF source code to bring in this brand new variable. We're not going to say inside of this example how that field is constructed, though you could use the real program to do it. That's exactly how we bring in the SST update data for the WRF model currently. But the modifications to the registry to say I have a new variable, that's a state data set. The modifications to say I would like to activate my new scheme, that's the namelist option, that's an rconfig piece. The modifications to the registry to say here is the name of my variable or my scheme, the enumerated type that I'm going to use inside of the physics option, that comes via the package. The registry changes and a few if tests inside of the specific driver, in this case the surface layer driver, are all that is required for us to process this data. We didn't go into what the new surface scheme actually did. We simply just assumed that there was a shell and that routine existed. But the part where the data gets into the WRF model was not discussed because that is handled automatically via the WRF code because of the way that we set up the registry with the auxiliary input stream being number 4. This last example for this presentation shows us how we can take advantage of some of the 4D arrays that are inside of the WRF model. The WRF model has a 4D array for all of the moist species, vapor, cloud, rain, and that's called moist. The WRF model has a 4D array for the scalars, number concentration for a number of fields. There's a 4D array for chemistry. There's also a 4D array for tracers. These passive tracers do not impact the model's solution. They certainly slow down the model because of computation and because of memory access. However, there is no impact to the model solution utilizing these passive tracers. The example we're going to show is a plume from the Fukushima event. What we're going to do is generate a model solution, center it over the Fukushima site, and then run a short 3-day course resolution forecast. What we're going to do at every time step is we're going to take the first few rows, or the first few vertical columns over the grid cell where Fukushima is and initialize that value to 1. And we leave the rest of the entire domain alone. So it's almost like we're doing a little puff model at every WRF time step. And that data gets advected and diffused and moves around through the simulation. To do this, there are only a couple changes that we make in the registry. We already have a 4D array called tracer. We simply go down to the tracer inside of the registry, and there are a number of components already. And we simply add one. Our new component name is going to be called plume. So we make a copy of one of the tracer components, and we edit so that previous name of a component, and when we swap in plume, we change the name of the variable that's going to be in the netcdf output file, which is uppercase plume. And then for the description, we just call it the Fukushima tracer, and there really aren't any units because this is just a passive tracer. We're setting a value to 1. We could have set it to 1,000 or 17. Because this is a 4D array, no 4D arrays or no components of any 4D array are ever allocated unless specifically requested in a package. So we make a package, we call it tracer test number 3, because we're going to use tracer option number 3. And then the variable that is going to be allocated if we ask for tracer option number 3 is going to be from the 4D array tracer. The component is going to be plume. So the syntax is package, the enumerated type that it's going to be tracer underscore test 3, and that value would be 3 because we're saying tracer option is equal to 3. So if the namelist option is equal to 3, we are going to allocate space for the plume component of the 4D tracer. Those are the only 2 changes that we make in the registry. The first one is we define the component of the tracer that we're interested in. And the second is we are going to define what namelist option activates utilizing that tracer component. The source code changes are also fairly simple. We have a domain that is 100 by 100. And again, that's just to make things very simple for us. In 2 locations, we're going to set a value of this tracer. Inside the real program, we're going to initialize the entire array to 0. And then we're going to take the ij location, which is associated with Fukushima, and we're going to take the first 5 levels and we're going to set that to the numeral 1. So the entire domain is 0 except for over Fukushima, and a small puff is going to be the value 1. 1 through 5 approximately represents maybe half of the boundary layer. Inside of the solver, we do the exact same do loop. Inside the solver, we're going to say if we are at the grid cell that is associated with Fukushima, so in this case it's grid cell 5050, we're going to take the tracer array, the 4D array, and we're going to use the component that is plume. And the syntax for that in WRF is P underscore and then the name of the component that we asked for in the registry. So the only change we make in the WRF model is every single time step we reset the first 5 values that are on top of Fukushima to the value 1 in our tracer, and we leave the rest of the tracer alone. So we're adding a continuous source over Fukushima that's coming out. To activate this option at runtime, inside of the namelist, we have the Dynamics namelist record. We have tracer option equal to 3. And we have a max domain entry, even though we're just going to run a single domain. So at runtime, if we ask for tracer option number 3, that's going to allocate space in the 4D array tracer for the 3D component called plume. Inside of the solver routine, if we activate that plume variable, we're going to puff a value over Fukushima at every single time step. So there's a 2-line change inside of the registry. The first to declare that we have a new 3D array plume that's part of the 4D array tracer. We have a package set up which maps or associates the tracer option equal to 3 to the particular 3D array plume that we are interested in. And we have a do loop source code change that we have to put in the solver, and simply every single time step we add a source term over Fukushima. The end result is, this is an hourly output of a non-dimensional plume variable that's being emitted from the Fukushima site. So again, it's important, only a couple lines of changes in the registry and 1 do loop in the solver are required. The purpose of this presentation was to give a sampling of the capabilities that are available from modifications to the registry. The first example actually showed how to not use the registry, that there are easy ways to provide input and output to the WRF model, and mostly its output, without modifying the registry. There are runtime options that allow you to associate particular variables with auxiliary streams. A nice example is if you have a very long forecast with a very large data set. If you would like to see output for a few variables at very high frequency, you can add those variables into a separate output stream at whatever frequency you would like without over-encumbering your disk system on your machine. So you can have your meteorological data come out every 6 hours for your 10-year simulation, but have data every 5 minutes for something, for example, like precipitation. Examples 2 and 3 are really pieces that you probably want to become familiar with. Example number 2 allows you to add a variable to the name list. This is the keyword rconfig. If you're ever interested in knowing what a particular variable inside of a namelist.input file is doing, simply go into the registry directory and look for that variable name under the rconfig keyword. Similarly, if you would like to stick an array into the model, or traditionally what most people want is to get an array out of the model, that's using the state keyword inside the registry. State allows you to allocate an array, and importantly, it describes what that array is, real, integer, logical. Typically, it's real. Whether it's a 1D, 2D, or 3D array, and 2D or 3D tend to be what most people are interested in for physics. Almost all arrays that go into the WRF model from external developers are for physics arrays. So the dynamical core for that, or the use for that, is MISC, miscellaneous, and the time level is 1. The staggering for almost all, or for all physics arrays, is a dash because it's not cell-face. It's not X, Y, or Z, which means it's not the variable U, V, or W. The input and output, how the variable is handled in nesting, those are all very specific to the variable that you have. And the easiest way to handle that for an array, the easiest way to handle namelist choices, is to find an example already in the source code very similar to what you want and make a copy of that line in the registry and then edit that line. Example number 4 showed a few ways that there are subroutines and functions inside of the WRF model that are built in that allow you to do some reduction type processing that lets you compute information on your local MPI process but still have access to domain-wide values, sums, averages, maximum, minimum, etc. Example number 5 also tried to wear a number of different hats. There's examples of how to do I/O. There are examples of how to treat a package, how to use the case statements inside of the specific drivers, how the physics driver gets the data dereferenced to it by the calling routine, either first RK_part1 for all the physics except for microphysics, or how the solver dereferences data for the microphysics driver. Also inside of the physics package, we saw the examples of how we are supposed to make sure that if a variable is optional, that we always use the present clause. The last example was for utilizing 4D arrays inside of the WRF model. Tracers are passive tracers inside of the model, so there are no feedbacks to the model solution, though it does take more memory and it takes more time to advect the additional scalars around. The last important reminder about example 6 is that even though we were talking specifically about tracers, the rules apply for all of the 4D arrays. No 3D component of any 4D array is allocated or available to be input, output, or communicated unless that component of a 4D array has been specifically mentioned in a package. So for example, the microphysics schemes, there are about 15 or 20 3D arrays that are available for the various microphysics schemes. The mass-based mixing ratio values, the number concentration values. None of those are allocated except via a package statement which associates that particular 3D array component of a 4D array with the runtime option that comes from the namelist choice. If there are any questions about this presentation or any of the other presentations in the rest of the WRF modeling system tutorial, please go ahead and send those to the WRF forum. There's a general statement for the WRF user support that is provided, and there are a number of resources that a user can take advantage of. WRF has a nice homepage that details not only information and documentation, but also schedules and availability of tutorials and workshops. Finally, the WRF and WPS source codes are maintained with an open development capability on GitHub at the following locations: